Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to show you how we can use function simulation to get quality maps that we used before when we are working with a custom piece that we draw in BeamTool. In the previous videos, we introduced the concept of point-to-spec function simulation and show you how we can use quality maps that we can get from point-to-spec function simulation to design an optimum inspection technique. If you haven't had a chance to review that content, I recommend that you first go to the previous videos, and when you get yourself familiar with these concepts, come back to follow this video. For showing you the example of using point-to-spec function simulation with custom pieces, we want to take advantage of an example of an inspection technique that we designed for one of our clients. The technique was for inspecting wind turbine main shaft, and the problem was that in these main shafts that can be as thick as 135 millimeter, sometimes we can have a problem of cracking right under a bearing housing. And the issue with this crack is that it can move from its nominal position, which is right at the corner here, but about plus or minus 15 millimeter. So we really want to have an inspection technique that can be sensitive to this axial drift of plus minus 15 millimeter and also cover the whole section of 135 millimeter of thickness. And obviously this can be a very big region for any FMC, TFM, or PCI inspection. So we will want to design ideally a phase array technique that can be sensitive to see the facets of this crack in the direct incidence, and so that it can track the extent for sizing. And note that here we cannot also take advantage of any beam skipping because of the very large travel path. So let's go to this example. So first of all, in BeamTool, we need to deal with a custom piece. So we go on a piece and select custom. And here we know the velocity of the piece that you're going to deal with would be what is there by default in BeamTool for steel, because that's a steel shaft. Then we can import a drawing of this shaft or the image of the shaft with a dimension. And we just put it with just a random scale here. And here the important factor would be that this depth or this dimension is 135, and this angle, the shaft body here, angled by around 5.74 millimeter. So first, to be able to deal with this geometry, we can come to tools and click on the image and come to the tools. And first, let's say move drawing to the origin. This tool helps us to choose which part of this image we want to set exactly at 0, 0. And my choice would be the corner here would be the location that the wedge can be closest to. So I can zoom in and click on this point. Right now you see that it's around like 12 and 12. But as we click on this, basically it shifts the drawing, this point of a drawing to 0, 0 that I can use as my origin. The next thing I can do is to come here and use interactive scale. And then the goal would be to make sure that this distance be exactly as the true dimension specified by drawing, which is 135. So I can come and click on this point on top and then zoom in at a point at the bottom here, let's say. And BeamTool tells me that currently this dimension is measured as 46.69, but now we can put the actual distance, which is 135 millimeter, and say scale the geometry. And when I do that, now you notice that this is now scaled properly. So this is now a piece, the drawing actual dimensions of the piece that I'm going to deal with. Now my next move is to draw lines on top of this geometry, on top of this image, to define the geometry that I want BeamTool to consider for any simulation or any beam interaction. So to do that, I come to add geometry and I choose a line and go and try to draw a line directly on this top, which can act as my surface. And also I can draw another line at the bottom here to act as basically the bottom surface. Now, when we have these two lines, we can add our probe. I come here and I go to phaser probe, and you can see that my phase probe show up here. I can flip it to the other side, and then I can add the probe I want to use. For this example, I'm going to use a 7.5 megahertz L60 PWZ1, which is a 7.5 megahertz probe. The pitch is 1 and 60 element. It's a large aperture probe because I have in mind that I want to take advantage of the focusing that will always help to have higher frequency and larger aperture. To go with this probe, I use the wedge SPWZ1N55S that creates a nominal 55 degree shear. So now the next thing is to position this on top of this face. I know by my drawing that this line is angled at 5.74. So to begin with, I can just also tilt the wedge 0.74 here by the same amount. Then I can move it up to exactly match this line. So now at this point, we draw a line for our geometry, we put our wedge, and we can be ready for simulation. Before that, I need to add a beam set. So I use a sectorial beam set here. And the idea is to cover this extent here and also take advantage of focusing. So first thing I do, I use 60 as my aperture, meaning that if I choose to display elements, I'm using all my elements for beam creation and focusing. Now I can set the range of angles. Let's say I need around, start from somewhere like 36 millimeter and go up to cover this, let's say around 85 millimeter. And notice that here we only have a chance to hit this potential crack indirect, so that's why we need to go to very high angles, although we know that in some cases they are not steered very properly or ideally. Now the next step here would be to add a focusing. Here I can come and choose a projection focus. These points start to show up here on the angles, and that's where it shows the focus length. And I can increase the focus length until the focus length matches, and you see that these purple points are moving back and forth until it matches at the offset that matching the nominal location of the crack, here. So now that I have this, set up, the next step what I need to do is to see how I can do the simulation. So I can come here and first try to say I want to do this simulation on vertical resolution. But the problem here would be if I set to run, BeamTool would not know where I chose this line to be as my geometry. So the first thing I do is I can turn off this beam and I can move my drawing away for a second. And then you can go to the piece, just go to this whole thing, go to the piece, and here you need to specify which of these lines is your front wall and which one is back wall. So for instance, for now I want to choose front wall. So I say choose, and then here, because it's not the full body, I can choose just this segment. So I say choose a segment instead, and I come here and as I move my mouse on the top line, it becomes Greek and I can click on it. And then BeamTool will add that line in the custom piece configuration as the front line. And as you see, as I move on it, it becomes highlighted. Same thing I can do for my back wall. I can choose a segment and I can come on the bottom line, click on that, and now BeamTool will consider that as the back wall or bottom line. So now I'm ready to do the simulation, except still, so I can bring this back now to where it was, and I can turn on my beam set, except that when I'm on the skip, because I haven't specified any extent to my geometry here, BeamTool will basically infinitely make a very infinite travel distance because everything is on skip. So to make this more realistic, what I will do is to specify exactly the travel path that I want my simulation to run. So I can come here and change skips to distance from the element. And when I do that, I can keep increasing the distance until my beams cover the area that I'm interested. So here in this case, if I choose this to be 190 millimeter, seems like I have a good coverage to the region that I'm interested to look at. So at this point now, I can go to my simulation and PA quality tab, vertical resolution, and say run. And when we hit run, it's a large area, so we need to wait for this to render. It's going to take a little bit longer, and we'll wait for the simulation to complete. Okay, now that our simulation is complete, I can also have an option to show beams. And the main thing that I want to pay attention here is that knowing that from this location, which is a nominal location of the crack, we will have plus minus 15 millimeter offset potentially, I'm looking at my vertical resolution and see that this vertical resolution is kind of fairly consistent if I move plus or minus 15 millimeter. So although I know that my focus is best right at where the focal points are chosen, but this axial drift of 10 to 15 millimeter do not seem to make a large or huge difference. And I can see that also on the map also. So what this tells me is that if I choose this sectorial beam set and choose the focusing right here with all the aperture, my focusing quality is such that I can remain sensitive to positional variation of this crack for plus minus 15 millimeter. And then that tells me that this can be a good technique to use here. Now, to just see the example of the inspection result, I'm gonna load the inspection results here for you. So here, this is actually a inspection result of with the cracked shaft with the current technique. I'm gonna also load image of the cracked shaft. So here, and let me just move this drawing away for a second. So here we had a shaft that was given to us an example that was actually cracked and all the way through. And you can notice here, even on this image, that how the axial position of this crack essentially drifts by that plus minus 15 millimeter. But also now you can notice that with this focus technique, we were sensitive to the facets of this crack such that here, if I move this here and I turn off the beams for a second, and obviously this needs to be angled and scaled properly. Okay, you will notice that we basically could trace the facets of that crack all the way through. I can also turn off the simulation so you see all the beams. So this needs to be moved all the way here, and the image can also move back here as a reference where the crack was essentially. So you now realize that with this technique we could easily trace all the facets of this crack and also be sensitive to the index position change of the crack, because our vertical resolution map showed us that we don't have that much of a change. And I hope you understood here how we can use this custom geometries for using this pointer function. The main thing would be that after we draw our piece, we specify the front wall and back wall to BeamTool for the simulation, and then the rest of the simulation tool can go as used before. I hope that this video was useful too. Thank you.